This video is brought to you by mywayteaching.com.
So now coming to the last part of this chapter, that is rolling motion. One of the most common motions observed in our day-to-day life is rolling motion. All wheels used in transportation, they have rolling motion. For specificness, we shall begin with the case of a disc, but the result will apply to any rolling body rolling on a level surface. Okay, we shall assume that the disk rolls without slipping. This means that at any instant of time the bottom of the disk, which is in contact with the surface, is at rest on the surface. So we have remarked earlier that rolling motion is a combination of what? Rotation as well as translation. We know that the translational motion of a system of particles is the motion of its center of mass. See, let VCM be the velocity of the center of mass and therefore the translational velocity of the disk. VCM, you can see here, this is VCM. This is the velocity of the center of mass and therefore it is the translational velocity of the disk. Since center of mass of the rolling disk is at its geometric center, VCM is the velocity of C and it is parallel to the level surface. The rotational motion of the disk is about its symmetry axis which passes through C. The rotational motion of the disk is about its symmetry axis and that axis which it passes through this center C. Okay. Thus, the velocity at any point on the disk, like it can be at P naught, we can consider different particles at P naught or at P1 or at P2. It consists of two parts. One is the translational velocity VCM and another one is the linear velocity VR on account of rotation, because it is the combination of both translational and rotational motion. So, the magnitude of VR is nothing but RW, where W is the angular velocity of the rotation of the disk about the axis and R is the distance. R is the distance of the point from the axis, that is nothing but from C. R is the distance. So the velocity VR is directed perpendicular to the radius vector. So VR is directed, you can see here it is perpendicular to the radius vector of the given point with respect to C. So in this figure, the velocity of the point P2, that is the velocity of this point P2 is what? That is V2 and its components VR and VCM. The components of this V2 are VR and VCM are also shown. So that is perpendicular to CP2. It is easy to show that VZ is perpendicular to the line P0 and P2. So P naught, if you consider the line P naught and P2, VZ is perpendicular to these two. So therefore the line passing through P naught and parallel to W is called as instantaneous axis of rotation. Okay, which is parallel to W and which will pass through this P naught, that is called as instantaneous axis of rotation. At P naught, you can consider the linear velocity due to rotation, that is VR, is exactly opposite to the VCM, that is translational velocity. The magnitude of VR is given by RW. At this point P naught, the magnitude of this VR is given by RW, where R is the radius of the disk. The condition that P naught is instantaneously at rest, it requires VCM to be equal to RW. Thus, for the disk, the condition for rolling without slipping is VCM must be equal to RW. Okay. So, incidentally, this means that the velocity of the point P1 at the top of the disk V1 has a magnitude VCM plus RW or 2 VCM and it is directed parallel to the level of surface. Okay. This is all about the rolling motion. Now let us consider kinetic energy of rolling motion. Okay. the kinetic energy of rolling motion. So, the kinetic energy of a rolling body can be separated into kinetic energy of translation and kinetic energy of rotation. So, this is a special case of a general result for a system of particles, according to which the kinetic energy of a system of particles can be separated into the kinetic energy of motion of center of mass, that is mv square by 2, and the kinetic energy of rotational motion about the center of mass. We can separate those two no, kinetic energies. So we can write k is equal to k dash plus mv square by 2. So we assume this general result and apply it to the case of rolling motion. In our notation, the kinetic energy of the center of mass, that is nothing but kinetic energy of the translation of the rolling body, is given by m vcm square. The kinetic energy of this rolling motion is given by this, where m is mass of the body and vcm is the center of the mass velocity. Since motion of the rolling body about the center of the mass is rotation, k dash represents the kinetic energy of rotation of the body. So that k dash is given by iw square by 2, where I is the moment of inertia about appropriate axis, which is the symmetry axis of the rolling body. Then we can consider the kinetic energy of the rolling body as a whole, that is given by k is equal to k dash, that is given by iw square by 2 plus, instead of mv square by 2 we can write it as 1 by 2 m vcm square now, isn't it? Substituting I is equal to mk square, where k is the corresponding radius of gyration of the body and vcm is equal to rw. K is equal to 1 by 2 mk square vcm square by r square plus 1 by 2 m vcm square. So if you take 1 by 2 m vcm square common, we'll get 1 plus k square by r square. Okay. So now let us consider a simple problem. Three bodies, a ring, a solid cylinder, and a solid sphere, roll down the same inclined plane without slipping. They start from rest. The radii of the bodies are identical. Which one of the bodies reaches the ground with maximum velocity? So, we assume conservation of energy of the rolling body, which means there is no loss of energy due to friction. That is an assumption. The potential energy lost by the body in rolling down the inclined plane is given by the potential energy lost in rolling down the inclined plane is given by mgh is equal to the kinetic energy gain, isn't it? So since bodies start from rest, the kinetic energy gained is equal to the final kinetic energy of the bodies. So we know the equation, that is k is equal to half mv square 1 plus k square by r square, isn't it? Where v is the final velocity of the body equating k and mgh. See, the potential energy lost is equal to kinetic energy gain. If you equate these two, we get V square is equal to 2GH 1 plus K square by R square. So note, it is independent of mass of the rolling body. For a ring, if you consider ring, in that case K square is equal to R square. So V ring is equal to, in that case if you substitute K square is equal to R square, we'll get square root of 2GH divided by 1 plus 1. That is equal to square root of GH, isn't it? And if you consider a solid cylinder, then we'll get K square is equal to R square by 2. So we can consider V ring is equal to square root of 2GH by 1 plus 1 by 2. So we can write it as square root of 4GH by 3, isn't it? So if you consider a solid sphere, that is K square is equal to 2R square by 5. P sphere is equal to square root of 2GH plus 1 plus 2 by 5. So that is equal to square root of 2GH 7 into 5. Square root of 10GH by 7. From the results obtained, it is clear that among the three bodies, the sphere has the greatest and the ring has the least velocity of the center of mass at the bottom of the inclined plane. Okay, from these results, we got for the ring the velocity that we got for ring is square root of gh, and the velocity that we got for disk is square root of 4gh by 3, and the velocity that we got for sphere is square root of 10gh by 7. So from this it is clear that the sphere has the greatest and ring has the least velocity, isn't it? Okay, suppose so we discuss intermediate between this ring as well as sphere. So here in the figure they have given this inclined plane with the different ones. We should consider ring, then disk, then sphere. So it rolls down from this inclined plane, and we have calculated the velocity, and even we have compared the three different bodies.